Manhattan's Citicorp Center. A hurricane threatened to bring it down on some of the most crowded streets in New York City. Only one engineer knew how to stop it. The Titanic, hailed as unsinkable, she took 1,500 to a watery grave. Now scientists shed new light on an old mystery. The MGM Grand Hotel, and the search for why so many died 20 stories above the flames. Engineering disasters. Las Vegas, Glitter Gulch. The city thrives on tourism, luring millions of visitors with the promise of glamour and gambling. In 1980, one of the biggest casinos in Vegas was in the MGM Grand Hotel. The gambling hall was longer than a football field, with 40 blackjack tables and 1,000 slot machines. But on the morning of November 21st, the casino's luck ran out.
In Las Vegas this morning, a huge fire is raging out of control at the MGM Grand Hotel. Many of the guests are still in their rooms and are calling and waving for help.
I looked up and I was just amazed. This huge building, which at that time was the largest hotel in Las Vegas, just smoke pouring out of windows and doors and out of the roof area.
The blaze was one of the worst hotel fires in U.S. history. 85 guests and employees died, and another 600 were injured. Ironically, the hotel had passed a fire inspection just 6 months earlier. What chain of events sparked this huge fire and turned the glittering casino into a smoldering cavern? It took teams of investigators and some of the top fire scientists in the country to solve the mystery of fire and smoke. Harvard University's Howard Emmons was one of the first scientists to study how fires spread through buildings. The MGM's insurance company asked Emmons to investigate the fire and help recoup their tremendous losses.
They wanted their $150 million back from somebody who was responsible for the fire.
Emmons began studying thousands of pages of eyewitness accounts. To pinpoint responsibility for the blaze, he needed to know how the fire started and spread.
Lay people are not good observers, especially if they're running for their life. And so you got many contradictions. But by reading them carefully, you could sort of piece together exactly what that fire did.
Witnesses said the fire began next to the casino in a small restaurant called the Deli.
It was started by the electrical connection to a little compressor that cooled a pie rack.
An employee passing through that area noticed it, ran to call for help. Then he ran to get a hose line and brought it back into the area, and he was going to fight the fire. And by then it's breaking out, starting to involve the ceiling area, and so they fled.
Like these wood chips, the Deli's wood fiber ceiling began to warm. As the wood grew hotter, it decomposed, releasing hot combustible gas. It is the gas released during a fire that burns.
The fire in the Deli became quite severe. The ceiling then radiated the booths. They got ignited and the fire became pretty furious. Within a matter of seconds, perhaps a minute, everything in the room is burning. And we've reached what the firemen call flashover.
Flashover is an event in the growth of a fire when the room in which the fire started becomes totally enveloped in flames. A small fire is gradually heating up the materials in the room at a growing pace, and there comes a time, only perhaps 2 minutes after the fire started, when all of the combustibles in that room have given off enough combustible gas to where those combustible gases ignite simultaneously and the room becomes an inferno.
Emmons concluded that once the deli flashed over, hot smoke and flame poured out the doorway and into the casino. Firefighter Bert Sweeney.
I was at Station 11 across the street from the MGM. Between 10 and a quarter after 7, we got the alarm. We geared up and responded.
Sweeney and 3 other men arrived in just 2 minutes. They walked through a side door into the casino.
We looked over, and there was a string of smoke that was probably about 2/3 to the height of the ceiling that had fanned out. And just as we got down to the casino level, the fireball broke out of the delicatessen with people scattering like flies.
Hot smoke and flames from the deli ignited the mirrored plastic on the casino ceiling. Waves of fire rolled through the cavernous room.
It was like a Hollywood slow motion special effect, the way it came out. The front perimeter of the ball was intense black smoke, and there were just little fingers of flame that would erupt out of it. They probably had 2 or 3 steps before the ball went over them.
In about 5 minutes, it raced down the ceiling of the casino, lit various pieces down below. Beautiful, but boy, did they burn.
I was the last one out, and I looked down, and the entire end of the hotel was engulfed in flames. And it was like, wow, it's just absolutely incredible.
The fire destroyed the casino and killed 7 people there. What could have fueled the deadly blaze? Emmons knew the answers lay in the ashes of the deli, and he targeted 2 major suspects: the flammable polyurethane restaurant booths and the wood fiber ceiling tiles. With the aid of a computer simulation, Emmons investigated the 2 suspects. No one had ever used a computer to model an actual fire before. The problem was complex, with hundreds of variables. Emmons first needed to learn how quickly the restaurant booths and ceiling tiles would ignite, burn, and extinguish. Today, this type of information is gathered from all sorts of common materials at the Worcester Polytechnic Institute in Massachusetts. David Lucht directs the program.
Predicting how fires will behave in buildings is a very complex engineering problem, and we have to start with very small pieces of information of this size. This apparatus is called the cone calorimeter. It exposes a sample of combustible material like plastic or wood to a radiant heat source, and it gradually gets warmer and warmer until it ignites. Ignition. And what we're trying to determine is the material properties of each material, such as how much carbon monoxide it produces, carbon dioxide, smoke, and rate of heat release.
Emmons gathered similar burn data on the ceiling tiles and restaurant seats, then plugged the information into the computer. The simulated deli burned just like the real one.
Checked pretty well with what I had learned by reading all the depositions. So I said, okay, I guess the model's good enough to tell me something that really counts.
Emmons ran the simulation twice more, once without the polyurethane booths, once without the ceiling tiles. Soon, he had his answer. The computer model revealed that the ceiling tiles and seat cushions were both responsible for the flashover. But that wasn't all. Emmons discovered that the deli air conditioner had switched on during the fire. Had it fanned the flames? He ran the simulation again with the air conditioner turned off. The deli still flashed over. The air conditioner was not responsible for the inferno. So the computer program had successfully modeled the fire, but it only explained the deli. It wasn't sophisticated enough to model the fiery casino or the smoky high-rise.
I want to be able to solve the entire MGM problem, the whole hotel. But you need a mighty big computer if you're going to do that whole building.
The rest of the towering hotel was beyond the reach of Emmons' simulation. Unraveling that mystery would take another scientist and old-fashioned detective work. Seven people died when flames gutted the first-floor casino. But as firefighters evacuated the top floors of the MGM Grand Hotel, they found 65 more bodies. What killed these guests 20 floors above the flames? Dick Custer was a fire research engineer for the federal government. He arrived in Las Vegas the day after the fire and saw smoke still hanging over the ravaged hotel.
I just couldn't believe it, seeing this incredibly massive amount of smoke coming from a modern hotel. This was the sort of incident that is perhaps once in a lifetime in the history of a firefighter. I've never seen a fire of this magnitude before, certainly not with this severe loss of life.
No alarms rang on the upper floors of the MGM, and many guests learned of the danger only when fire trucks arrived. By then, people were already trapped.
As the fire department rolled up on the scene, there were people actually leaning out of the windows, standing on balconies, screaming for help, many people waving towels and sheets to attract attention.
On the 22nd or 23rd floor, we came to the elevator lobby, and at one point there was 5 or 6 bodies just laying there. They were covered with black smoke and soot, and the soot was so thick that if you would pick up an arm, there would be the perfect clean outline of a hand on the carpet. And it was obvious they died there, overcome by smoke, waiting for elevators that never came.
Others struggled through the smoky hallways to the stairs, but half the stairways were clogged with smoke. Guests were trapped when the doors locked behind them.
Fires generate huge volumes of jet black smoke that's laden with lethal carbon monoxide. And even in the daytime, it could be like pulling the shades down and turning off the lights. The smoke is so black, and you're breathing the noxious fumes and start to get disoriented, and it's just a lost cause after that.
Custer searched the empty hotel to track the path of the deadly smoke and uncover how it had raced through the building.
One of the mysteries was how the smoke traveled from the casino up to the floors where the people died.
Custer's first clue came in an elevator lobby. He found wispy patterns of soot around the buttons. He had his first suspect, the elevator shafts. Next, he rolled out the hotel's blueprints and found another suspect. The hotel's wings were separated by tall seismic joints, designed to let the building flex during earthquakes. He searched the hotel and found the joints burnt and sooty.
Between the buildings are tall shafts that extend from the casino all the way up to the top of the building. Smoke and hot toxic fumes boiled up these shafts and came out through openings on each floor.
The seismic joints in elevator shafts acted like plugged chimneys. The smoke rose up the tall shafts and poured into the hallways. Custer climbed to the hotel's top floor and found one more culprit. The air conditioner had safety doors, called dampers, that would snap shut to limit the spread of smoke. The dampers would activate when they sensed the heat of a fire, or, in this hotel, the heat of the desert sun.
They were getting such high ambient air temperatures that the sensing dampers were closing, shutting down the entire system, and It's my understanding, as a cure for this, maintenance personnel took lag screws and mechanically fastened the dampers open, thereby negating their effect.
The propped open air conditioner, the elevator shafts, and the seismic joints filled the upper hallways with noxious smoke. 22 guests choked to death while struggling to escape. Other deaths were more mysterious. 25 died in rooms, some with no obvious traces of smoke.
When you go into a room that's absolutely clean, and the people are there under no distress and no panic, and yet they're not alive, well, it's disheartening for one thing, and then, man, you want to know what happened here. I mean, we've got to know what happened here.
What I saw when I came into this room was what appeared to be a surprising lack of smoke. The walls and the ceiling and the floor did not appear to have any noticeable stains. Some of the bodies were found stretched out on a floor or perhaps seated, showing no signs of any anxiety or stress, just simply died in place. In one instance, a couple was found dead on the floor in their hotel room, and they were in a relaxed position as if they had just laid down and gone to sleep. In looking at the guest rooms, I noticed that the air supply came through small grills over the top of the guest room doors. I removed several of these grills and noticed that the air filters behind the grills were tightly packed, literally clogged with heavy black soot particles.
Custer discovered that the room's air conditioners had drawn air in from the smoky hallways.
The thick black smoke had been absorbed or filtered out by the air filters, but that wasn't enough to filter out the toxic carbon monoxide and other gases that killed the occupants. They were overcome very slowly, primarily because of the narcotic effect of the fire products. It's almost like being put under anesthesia in the hospital. They probably had no idea that there was anything toxic. They would have smelled smoke, but they wouldn't have seen smoke.
The invisible, poisonous carbon monoxide replaced the oxygen in the victim's blood. Their central nervous systems slowly shut down, lulling them into a deadly sleep.
This is truly what would be called an accident, where a huge number of small items all came together at the same time and resulted in a disaster.
Bad luck turned relatively minor defects into a major catastrophe. The flammable deli booths and ceiling tiles, the locking stairway doors, the propped open air conditioner, and the smoke-spreading seismic joints all played a part in the tragedy. Six months after the fire, the MGM Grand reopened with a $5 million fire safety system. The hotel, now owned by Bally's, is considered one of the safest in the world.
What happened after the fire, more stringent codes were added to the fire code regulations. Bally's decided to go far and above the codes that did come out. We have over 1,250 system-generated smoke detectors. What I mean by that, they're all tied into a central computer. We have over 8,000 audio evacuation speakers. We have water flows and tampers and sprinklers throughout the building. We have over 30,000 sprinkler heads. As we know, the most dangerous thing in a fire is smoke. What we did is added pressurization fans to the stairwells. When an alarm comes into the central computer, these fans automatically turn on and pressurize these stairwells, which won't allow any smoke in, and everything gets vented out through the roof.
However, not all hotels are as safe as Bally's.
When you come to a high-rise building, you need to know where the exits are, how you can get into that building, how you can get out of that floor. Take a moment before you go into your room at night and think, where are the stairwells? How can I get down them? If I wake up in the middle of the night and it's dark, where do I go for help?
Well, there are times when I've had to stay in hotels that are unsafe, outside the United States and even within the United States. What I try to do there is get a room close to the exit and a room close to the ground level. And I guess I gamble a little.
The early 1900s was the age of great machines, and the Titanic was the greatest of them all, the biggest ship yet built. On the night of April 14th, 1912, the lookout saw a mountain of ice dead ahead and signaled the bridge. Hollywood depicts the collision as a mighty crash, but in reality, the ship just grazed the iceberg. Many passengers never felt a thing. How could this soft scrape sink the mighty ship? Today, a team of Canadian scientists has gone back to the Titanic. They've plucked from the icy depths a piece of the ship's hull. It's a clue to an 80-year-old mystery. What really sank the Titanic? Steve Blasko is a marine geologist. He organized a scientific team to accompany an expedition to the Titanic. He never dreamed he would come back with a piece of the ship's unsinkable hull.
Lots of people interested in this stuff as souvenirs, so we have to keep it hidden in the filing cabinet there. This is actually a piece. You can still see the rivet curvature here from where the rivet hole was. And it's just actually the edge of the plate that's left. Everything else has been consumed in the testing.
When found in a pile of debris just off the ship's bow, this piece was about the size of a dinner plate. But it has been whittled away by scientific testing in an attempt to solve the mystery. The trail of clues begins at the Titanic's construction, the height of the age of steel.
You got to sort of look at it in terms of what was going on in 1912 in the world. We were in fact starting to develop airplanes and more powerful locomotives.
Steel was stronger and cheaper than iron. With steel, engineers could fashion the frames for towering skyscrapers, the cables on the Brooklyn Bridge, and the massive Titanic. The ship's hull was built from thousands of steel plates, 10 by 30 feet long. Each plate was almost an inch thick. The hull was separated into 16 watertight compartments. 5 compartments would have to fill before the ship would sink. Her designers estimated that even in a worst-case scenario, the ship would take 3 days to sink, plenty of time to rescue all the passengers. The Titanic carried some of the richest and most influential people in the world. In the greatest of luxury, they steamed across the Atlantic.
Up until the ship hit the iceberg, it was a pretty standard cruise. I mean, the vessel was cruising along at its nominal speed of 21 knots, and it was going to New York. It was off on its maiden voyage, and everyone was feeling pretty happy with themselves. I mean, it's the classic Edwardian era, cruising off in ignorance of itself sort of thing, and smashing into this iceberg.
After inspecting the damage, the ship's builder thought the iceberg had ripped one huge gash along the hull.
With 1 and 2 holes, the mailroom and boiler rooms 6 and 5. That means a gash 300 foot long from there to there, below the waterline.
The Titanic sank in just 3 hours, 20 times faster than predicted. Too fast for rescue ships to arrive. New scientific evidence tells us why. The wreck lies on the ocean floor, 500 miles southeast of Steve Blasko's home in Nova Scotia. Blasko wasn't interested in why the ship sank. He wanted to learn why it didn't disappear into the mud when it struck bottom.
There's a lot of soft sediments on the bottom, and there's a good chance Titanic could have buried itself. What we found out is that, in fact, it didn't. So you have a 20-ton bow section sitting roughly on the seabed. They're only buried in 10 to 15 feet. And it became a real question as well, why didn't the Titanic disappear?
Blasco brought along his friend, Duncan Ferguson, who was interested in how steel corrodes in the deep ocean.
So when Steve first came to me and said, we're going to go look at the Titanic, do you want to come along? Well, it was kind of like a great Christmas present.
Steve Blasco took a submersible 2.5 miles down to the Titanic to take a first-hand look.
It was like going down at 2 a.m. in the morning and parking yourself in the front lawn of a haunted house. So you got this sort of real feeling of spookiness.
Blasco couldn't see the damage from the iceberg because it was buried in the mud. But on another dive, a sub brought back a piece of the Titanic's unsinkable hull.
We did not go on the expedition with the expectation of recovering a piece of hull plating. We were looking at biology, geology, chemistry.
This first time, a piece of Titanic. I got it.
It had been sitting in the sediment. It was sort of half covered in sediment, half not, and the submersible went by, sort of saw it, and went out with their arm, picked it up, put it in their tray, and they came up, and it was quite an interesting moment.
Ferguson recognized the shard as a hull plate because of the characteristic rivet hole and a smudge of red paint.
Which is great. That's a keeper.
To the mechanical engineer, the piece was more than a souvenir. It was a unique opportunity to investigate why the Titanic sank so quickly. He needed to learn the characteristics of the Titanic's steel, but wanted to conserve his precious piece.
We wanted to approach the testing of the steel very carefully because we had sort of a piece that nobody else had ever seen before, a limited volume. We couldn't do everything to it that we wanted to do. So we wanted to go through and test it really systematically.
Immediately, they found a surprise. This is a piece of normal steel. This is a piece of the Titanic. Both are magnified 100 times. The Titanic steel is granular and crossed with thin black lines.
There were all sorts of what we would call black stringers, and this steel was not homogeneous. It wasn't nice and clean and pure. There were these sort of big black streaks going through it, and right there you go, well, there's something wrong here. There's something that you wouldn't expect in modern day steel.
Chemists further analyzed the chemical composition of the steel. The tests revealed that the Titanic steel had a dangerously high level of sulfur.
And right away you could see that the chemistry was off. The chemistry was not what you would expect in modern day steel. Particularly the sulfur was way high.
Steel is made by heating iron ore to remove impurities and add other elements. In the process used to manufacture the Titanic steel, a coal fire melted iron ore, infusing the iron with carbon, sulfur, and other elements. Air was then blown over the molten metal, taking away some carbon, but leaving impurities like sulfur. Engineers today know that too much sulfur can make steel brittle, creating pockets of thin lines where cracks can begin. Was this the case with the Titanic? Ferguson ordered the test that would answer this question, the Sharpie test. The Sharpie test is a rather crude and old procedure, but it's quite effective. To start, a small piece of high-quality steel is put in a cold bath to simulate the conditions of the icy North Atlantic. Cold water can make steel more brittle. Jim Matthews, metallurgist.
The specimen is tested at a number of different temperatures to establish the temperature at which it will be ductile and to establish the temperature at which it will be brittle.
Ready, Jim?
Yes.
This is a piece of high-quality steel. It bent and stretched, but did not break. This means it is ductile.
When the samples are ductile. They do not come apart, and the surfaces have a very torn appearance, which is a sign of a lot of energy having been absorbed.
Then they tested the Titanic steel. The Titanic sample did not bend or stretch at all. It simply snapped. Further tests showed that the Titanic steel was brittle even in warm water. Duncan Ferguson constructed a new scenario of the Titanic's final hours.
Unfortunately, the ship hit the iceberg in the worst possible condition. If it had had it dead on, probably would have survived. Unfortunately, they just glanced it, and so the iceberg basically just rubbed along the edge. And because the steel didn't have any impact strength and wasn't able to absorb any energy, it just went through and went pop, 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 pop along every plate that it hit.
The iceberg scraped along the Titanic, causing many small cracks, not one huge gash. The cracks were only an inch or two wide, but ripped across a huge section of the hull.
The ship was basically filled up. The bow section, the first 5 watertight compartments filled up, and you have to realize that the other 11 to the stern were still full of air.
The air-filled stern remained buoyant as the heavy bow sank. The opposing forces began to tear the ship apart.
My great analogy is the loaf of French bread, because it's rather like the ship. And so it's now at 45 degrees, and it's being held here, and it's being held here, it's being pulled, and it's just breaks. And this is not doing exactly what it's supposed to do. But that's exactly how the vessel broke out, in that it broke here, and it broke here.
The ship ripped apart with a roar. The bow sank quickly to the bottom, and the stern settled 2,000 feet away. The midsection imploded, scattering debris across the ocean floor. Steve Blasco took core samples of the bottom to understand why the huge hull only sank in about 10 to 15 feet.
Actually, very silty clay. You can tell by just scraping it and tasting it. It's very gritty. Isn't it very gritty?
Tests indicated that the Titanic landed in an area of highly compressed mud.
Titanic is located here in the bottom of a valley, actually now called Titanic Canyon officially. The valley drains down into the subabyssal plain, which is very deep here, 20,000 feet water depth, the deepest part of the North Atlantic in this area.
The core samples revealed that the valley floor was packed hard. Blasco discovered why.
100 to 200,000 years ago, an enormous landslide moved through this area and removed about 100 feet of sediment, moved it further down in the basin, and left exposed very old dense sediments, which Titanic landed in 1912.
If not for the landslide, the Titanic probably would have disappeared into the mud. But who was responsible for the sinking? The scientists wondered if the builders were to blame for the brittle steel.
Of course, the first thing that runs through your head is, oh, scandal, someone's built bad steel, you know, and you wonder about what's going on. So I went back and did some research into just what were the standards of the day.
Ferguson concluded the steel was passable for 1912, but brittle fracture was not well understood at the time.
They did tests at the turn of the century, but they were very limited, and none of them had anything to do with the so-called brittleness of the steel. People were building as fast as they can, bigger than they can, we're invincible, let's just go do what we can do. At the same time, the steel industry was trying to keep up to this. They were developing new ways of making steel, and in fact, they were switching over just at this time. And it just appears that it didn't keep up. Now, that's what technology does, and that's often how technology evolves, is through failure.
It wasn't until World War II that engineers began to understand the problem of brittle steel.
These are the ships that carried the stuff for war. The fists and muscles and guns and tanks and planes that smashed the Luftwaffe.
These were called Liberty ships. Thousands were built to supply the troops overseas. But engineers were shocked when some of these new ships began breaking in two for no reason, some while sitting in dock. An investigation revealed that one of the reasons the Liberty ships shattered like the Titanic was brittle steel. The deaths of 1,500 Titanic passengers changed safety regulations internationally. Shipping lanes were shifted south, and ice patrols were established. Ships were required to have lifeboats for everyone and a 24-hour radio watch. But even today, say some engineers, ships still suffer from brittle fracture. The reality is that between 1912 and 1996, the steels that are basically being used in ships in the world are not that much better. Many of them are the same quality of the Titanic. As a consequence, we still see brittle fractures of ships. Matthew's conclusions are controversial because no records are kept on brittle fracture, so no one knows for sure how many ships sink each year from cracks in their hulls. But if Matthews is correct, engineers still have lessons to learn from the Titanic. The Citicorp Center in Midtown Manhattan is a landmark skyscraper. It is best known for its striking structure and angled roof, not its secret past. On Labor Day weekend of 1978, a hurricane moving up the East Coast threatened to break the tower in two. If Citicorp had collapsed, it would have been one of the worst engineering disasters in history. Thousands of tons of glass and steel would have crashed down on New York's crowded city streets. This is the story of a disaster that did not happen, and of an engineer who put his career on the line to stop a catastrophe. The story begins with a church, St. Peter's, the jazz church. St. Peter's was spiritual home to many jazz legends, from Miles Davis to Dizzy Gillespie. Back in the 1970s, the little church stood in the path of one of the world's most powerful banks, Citicorp. The bank wanted to demolish the entire city block to build its new high-rise headquarters, but church members didn't want to move.
We wanted to maintain our identity, St. Peter's Lutheran Church. We did not want to become the church at Citicorp. And so somehow we had to maintain our identity, so we had to seek separation from the high-rise building itself.
Bless thee for the love which hath created, doth sustain us from day to day.
The congregation finally agreed to an unusual arrangement. The decaying Gothic structure would be torn down, and a modern church erected on the same spot. The church sold the air rights directly above it for $10 million to allow the construction of Citicorp's $100 million, 59-story skyscraper. Civil engineer Bill LeMessurier was hired to find a way to suspend the giant skyscraper 5 stories above the church.
The whole problem from the beginning was an unusual one because the church owned the land on the north corner of Lexington and 54th Street, wanted to stay there, and we could build a building over them, but we couldn't come down to the ground on their site.
He decided to put the skyscraper on massive stilts, but to leave the corner open for the new church, the stilts had to be moved to the center of each wall. This in turn required a unique steel frame that directed the building's weight onto the 4 stilts. In a restaurant near his office, Bill LeMessurier came up with a design to accomplish this task. Citicorp's frame would be a series of 8-story triangles stacked one on top of the other. LeMessurier's groundbreaking design was light, economical, and elegant. But could the innovative structure withstand a hurricane? A skyscraper's worst enemy is the wind. The sides of a building are like giant sails. Even a slight wind can generate huge forces on the massive steel frame. LeMessurier sent his Citicorp blueprints to the wind tunnel at the University of Western Ontario for testing. First, a model of Citicorp was built. The plexiglass model was embedded with hundreds of tiny sensors that measured the wind pressure on various parts of the building.
There are hundreds of them all over the outside, and these can register the pressure at each one of the points where the holes are, and we can get a mapping of the pressures at any instant of time on the outside of the building.
To accurately simulate the wind striking the Citicorp tower, the entire city of New York was replicated for several blocks. To add greater realism, pseudo-buildings extended out for many more city blocks. First, the building was tested in light winds. The skyscrapers of New York channel wind like a canyon, creating whirls and eddies at street level. Engineers needed to see how these swirling winds would affect pedestrians. Then the scientists cranked up the fan. Engineer Alan Davenport is an expert on how wind affects skyscrapers.
Here we are standing in the middle of a wind tunnel with a hurricane coming at me and blowing in my face, and this is probably going to cause me to rock back and forth. In fact, it does. But in addition to that, there are forces that come from the side due to turbulence and other effects which are going to make me rock sideways. So the total combination is a mixture of rocking and twisting and rocking and rolling in the wind.
All modern skyscrapers are designed to be flexible and to move slightly with the wind. Citicorp rocked and rolled and survived. But the tests showed that on a windy day, the light structure would sway enough to make some occupants sick. LeMessurier developed a solution for this problem. It can be found at the top of the building.
This is the tune mass damper. It's a 400-ton block of concrete that was poured up here. It's used to dampen the effect that people feel of the building swaying.
As the building sways, the damper counters the motion, acting like a giant shock absorber.
The hydraulic system causes the 400-ton block of concrete to levitate. Once it's levitated, the actuators take over and they start to move the block in a circular motion with the building. This is the first building that had this design originally designed into the building from the get-go.
That's one of the extraordinary aspects of this building. Because we had a very lightweight steel frame, very efficient and economical one, that was made possible by using a mechanism to soften the motion of the building. It was an idea that had been thought about for bridges, used for bridges and so forth, but it had never been put into a building of this magnitude before. So this building is really a pioneer.
The complex opened in 1977 with St. Peter's on the corner and the tower high above. Headlines praised Bill LeMessurier and his innovative structure. The elation would not last long. 9 months later, LeMessurier received a phone call from a student studying the building's design. The student didn't understand how the oddly placed stilts could support the building. LeMessurier explained his solution, But the question raised another issue. He knew Citicorp could withstand heavy broadside winds. But what about winds striking the corners of the building? He hadn't tested the design in winds from this angle because New York's building code had not required it.
I was particularly interested in having the effect on the amount of the building moved. But just putting the numbers down in an organized way, I found something rather extraordinary.
LeMessurier found that if wind struck a corner of the building, the forces on the diagonal steel beams combined in a way he had not anticipated.
Half of the diagonals lost all stress whatsoever, and the other half doubled. I said, that's interesting.
Even so, he concluded the strong welded connections could take the strain. But further research revealed a problem. During construction, the plans had been changed without LeMessurier's approval. The beams had been bolted, not welded. Were the bolts strong enough?
When I really looked into the numbers, they were worse than I expected. And clearly they had not thought about the diagonal wind. It began to look a little scary to me.
In fact, LeMessurier was terrified. His calculations revealed that a strong hurricane would shear the bolts.
I came to the conclusion that these joints would break about halfway up the building and the building would go kerplunk.
LeMessurier notified the architect.
Well, that was a very sobering experience. I don't know that I felt such raw fear in my life before.
It was impossible to predict what might happen if the building fell. Hundreds of people might be killed. Several blocks of Manhattan could be crushed. Wind is a relatively new problem for skyscrapers. The Empire State Building, an older tower, will only bend a few inches in 100-mile-per-hour winds. The building is built like a fortress, with a heavy steel frame and thick stone walls. In 1945, an Army bomber crashed into its 79th floor. The skyscraper barely shuddered.
The 79th floor was hardest hit by the crash. Some people thought it was a Jap balloon bomb. When the plane hit the north side of the building, parts of it jammed in the structure and some plummeted down the elevator shaft, while other parts of the B-25 passed through the building, so great was the impact.
The Empire State Building's heavy frame and massive walls helped it survive. But as skyscrapers evolved, they became lighter and more flexible. Citicorp is half the weight of an equivalent skyscraper built 50 years earlier. Bill LeMessurier worried that his lightweight Citicorp building would be vulnerable to a major storm. It was August, hurricane season. Now, Bill LeMessurier faced a dilemma. His building was unsound, and he needed to make a decision.
Well, the fact that I was the only person that really understood this problem existed was a remarkable position to find oneself in, I'll tell you. And obviously the thought passes your mind, I could just keep my mouth shut. Maybe all trouble would go away. I said, what would I do to fix these things? Can they be fixed?
LeMessurier decided to call Citicorp chairman Walter Wriston, who took action to protect the people of New York and save his building.
After Wriston notified the mayor of the city of New York of the potential problem, the city really mobilized all of the forces, the police, the fire, the Red Cross, and they established an evacuation plan for an area within 1,000 feet or so of the building. All of this was being done in a very short period of time.
In the meantime, LeMessurier searched for a way to fix his building. He realized the weak joints could be strengthened by welding steel plates over them. Welders were hired to work at night while the building was empty. More than 200 critical joints had to be repaired, and the fix would take several months. LeMessurier worried. Could the building be fixed in time? Would a hurricane come?
We had weather reports every day. 3 different weather services. The reports were coming in every few hours, and there were alerts set up for any winds that would be over 40 miles an hour and so forth.
In the last week of August, LeMessurier got the call he'd been dreading.
Uh-oh, there's a tropical disturbance down there in the Caribbean. We had that about a week in advance, and it was monitored every day. And they usually don't come up the Atlantic coast all the time. This one did.
The tropical disturbance built into a hurricane, Ella. On September 1st, Ella was raging near the coast of North Carolina and heading toward New York.
The thing that would fail any building in New York is a storm whose center travels up through the harbor of New York. That would be the critical storm, and the storm was coming.
The welders were still months from finishing the critical repairs. As the storm approached, Bill LeMessurier worried. Would his partially fixed building pass the test? Or would his wonderful skyscraper be the first in history to collapse? Would he be transformed from engineering celebrity to engineering pariah?
Everybody in New York City had gone away on Labor Day weekend. I was almost there alone.
On September 4th, 1978, Mother Nature intervened. Hurricane Ella turned away from New York and spent its energy on the open sea. The danger was over. Bill LeMessurier contemplated his fate.
Hurricane always blows all the humidity out to sea with it. The sky gets blue. And so I sat there and listened to the fountain run and thanked the guy that had maybe driven me to do it right.
He will never know if his building would have survived. Repairs were completed, and today, Citicorp is believed to be one of the safest skyscrapers in New York.
You're not responsible just to your client, you're responsible to the public. And if the public safety is involved, that's the most important responsibility you have. And you must face up to it. At risk to yourself, don't even consider it, do it.
Today, St. Peter's remains tucked underneath the tower, continuing its tradition as a sanctuary for jazz. Above, towers a reminder of an engineering disaster that didn't happen.